Note, I think we should get a little bit started.
Yeah. Okay.
Hi, and hello to the internet. Come on, get a camera.
But I'm so tiny compared to. Okay.
Let me up just. There we go.
Okay.
Hi.
Welcome to EXAG, EXAG 4. I guess this is the 4th experimental AI and games workshop here.
Jeez, it's already been 4?
Yes, it's been 4. It's amazing.
Wow.
Yeah. So this year, Joe, James Ryan, who's not here, and I, Kristen, are the new organizers for this workshop.
Get in the frame.
Oh, I'm sorry. This is one. And so this year we've got 2 days full of papers, demos, short papers, a lot of cool stuff. And again, thank you all for coming. And if you're tuning in on the live stream, thanks for tuning in. So we're just going to go over a couple of logistical things before we start with the first couple of presentations of the workshop this morning. So let's see, what do you want to start with first?
Yeah, so first and foremost, as we've hopefully conveyed to you, EXAG this year is being live streamed again, but this time we are actually going to be capturing what's being displayed up here directly through this computer. Hence why we sent out a request for everyone to send your slides to me. So if you haven't done this already, please do so once you're at the stage when you're not, frantically updating them.
And if you would like to use your own machine for any reason, then talk to Joe. We can capture you on camera, but we won't necessarily be able to hook you up to the stream directly.
Yeah, it'll be a bit of a to-do, given that projectors are always weird.
And so a couple of other things. So for those of you who have not picked up a schedule, they're in the back. It's already wrong.
But if you go to the one on the internet, it's correct. On the
internet, it's correct. So just for all schedule needs, please visit exag.org/schedule. Some things minus the paper typos are two of the talks this morning are switched. So a vision for continuous automated game design will be going towards general RPG playing. And then break this afternoon will be an hour so that we can line up with the nice free AIIDE coffee break. So
because coffee is good.
Because coffee is good and you probably will all be tired. So break is going to be from 3 o'clock to 4 o'clock. And then we will start short paper sessions at 4:30 and go till 5:30.
Yeah. And a few notes on presentation. We have a webcam, but it doesn't necessarily have the best field of view. So you have about from here to about here to be standing. So just try to be mindful of that if you, like me, are someone who likes to pace when you talk.
And if for any reason you do not want to be on the live stream during your presentation, let one of us know and we'll turn it off. A couple other things. This year we are also upholding AIIDE's Code of Conduct. So if you go to the main AIIDE 17 webpage, they have their whole Code of Conduct there. Please make sure to follow this. And if you have any concerns, questions, any problems that come up, please talk to one of us.
Mm-hmm. And we will make sure it's taken care of.
Yes. So.
We're running way ahead of schedule.
Yeah, we were supposed to start papers.
Yeah, we got a question.
Where is the live stream? Where's the link for that?
I tweeted that out, but I can also, if you give me a few ticks, pull it up.
Okay.
Apparently there's an AIIDE Wi-Fi connection. Go figure.
And these will all be up on the EXAG YouTube channel after this. Which probably has nothing on it right now, but that's okay.
I mean, it's got the live stream on it, but that's it.
Yeah. It's now at tinyurl.com/exag17.
Nice. If you could tweet that out, that would be amazing.
Is there anything else that we need to?
I'm not sure. Right now, I'm just trying to pull up the live stream so I could see what chat is saying.
Okay.
Oh, that's good.
Okay.
Yay!
All right. Yay!
Cool.
So just, I guess, before we get started, a couple of quick acknowledgements. Thanks again to our co-organizer James Ryan, who is currently not here. He wasn't able to make it this year. So James, we love you. Hope you get to see this.
Yeah.
And then also thanks to Mike Cook, Antonio Lapis, and Alexander Zook, who is sitting in the back there.
Stand up. That's fine too.
We inherited EXAG from them, and they've been extremely helpful in helping us get this together, and lots of other small things like writing up paper summaries, giving us lots of great advice. So,
yeah, if you enjoyed
lots of thanks to them.
If you enjoyed the paper summaries, you can blame Mike because he basically set the tone for how the rest of those went.
Yeah. So yeah, if there are there any other questions or comments? I guess we can get started early and then.
Well, I want to give people a few minutes to send, make sure I get all the slide decks and stuff.
Thank you.
So if you are presenting before lunch today and you haven't sent me your slides, please do so. And I will take a few minutes. I'll kick the stream back to the going live shortly, and I will spend some time making sure I have all of them ready to go. So yeah, to anyone on the internet, see you in a bit. Hi again, everyone. Everything took less time than we thought, so we're going to get started with our first presentation. So here is another.
Hello everyone, I'm Ahmed. I'm going to talk about Marahel, which is a language for constructive level generation. And the brackets are kind of like fucked up a little bit, but it's because I have Arabic installed on my computer. So the first thing, what's Marahel? So Marahel is a descriptive language that describes 2D tile-based constructive level generator. First thing, Marahel means levels in Arabic, if no one knows about that. And what's the 2D tile-based games are games like this, like Super Mario, Zelda, which you can put all the objects, all the tile, like everything in the game on a grid of tiles. And constructive level generator, they are a type of generator where they don't take much time to generate stuff. Like they go one run over the stuff and they generate the output. They don't simulate stuff that's happening. They could after that check some constraint or whatever in order to improve the output, but they only go run an algorithm to generate the output. And these are two games that use some constructive generator, which is Rogue and Nuclear Throne. So why we are trying to do a level generation language? So one of the reasons we want to do is, if we have a level generation language, we can see the space of all these different languages, like different script and generator inside this language, and explore it and see if there is something new or something we didn't know about. The second thing is to simplify the development of the level generator, because if you have an open API, you can just experiment very fast, putting some generator together and see what's going to happen. So it's easy and it makes it easier to write your own generator. The third thing, which was the main reason for us, which we were trying to find another way to solve to try to tackle a general video game level generation problem, where you try to generate levels for any video game regardless what the game is. And we tried a couple of other algorithms, and most of them generate not good results. So one of the ideas is try to find a level generator in this space that fits a certain game using maybe an genetic evolution or whatever. So where exactly Marahel fits in the development, when you are developing a game and you want to use Marahel, where exactly it's there. So we designed the language to be totally independent from the mechanics of the game. So if you have a certain game, first thing you need to know what's the game mechanic in the game, and then you try to design your script to fit this mechanics. Like if it's a game you can jump in it, you try to put constraints in the way it's constructing the stuff to make the difference between two tiles, the height of them is not exceed certain distance. And after that you get a generated level, and you can, if it's a good thing, you can just output directly if you write a good script. Other than that, you can run another algorithm after that to fix it, or check if it's not good enough, you can regenerate and so on. So let's describe how the script and how the language is working. So this is the script in general. It consists of 5 sections, but we can divide them in 2 bigger sections. One of them is the level generator input, which are all the data that the Marahel will read and save it somewhere so to use it later, and then the program itself where it tries to execute and get the level in the end. So this is exactly what happened. So Marahel go first over the level generator input and read all the data and save it somewhere, and then it defined a 2D array of unknown values because it doesn't know what it has to put on the grid, the tile-based grid, and then first thing, it divided into specific regions based on the region sections that the user provide, and then after that, sequentially, it applies the algorithm that maybe get something like that, and then return this output to the user. So let's explain each section in detail. The first thing is the metadata. It contains just information about, in general, the level you want, the minimum dimension, maximum dimension. There is other parameters, but they're how it swaps, when it changes a value in the map, how it does it change it directly or generate it in a back buffer. There is other stuff you can add to the metadata to so Marahel can work with it. The second thing is the entities, and the entities are the object itself that will construct the main level. The level could have some player, treasure, like solid objects, enemies. So you have to define all the names that you are going to use or you want to generate or to put out at the end. And after that, you define something called neighborhoods, and neighborhoods are like relative location to a certain location. And in our implementation, we use like kind of like a two-dimensional matrix to represent that. Like for example, the all neighborhood here means that if you are at a certain location, you have to check all the surrounding location, all the 8 surrounding location. While the +1, it says if you are in a certain location, you have to check just north, south, and east and west locations for you. So these are the first part, which only have the input that the system is going to use later in the next 2 sections. The first one is the regions, and as I said like briefly before, regions are just parts of the map itself. Like it's not like the full map, it's just parts, because you could want just to apply certain generator in this part, not in the whole map. So it's a good way to define all the regions you want. For our current implementation, just use algorithmic region divisions, which are these 3 algorithms we just implemented, which the first one is equal division, where it tries just to divide the map equally based on a criteria, like dimension criteria, and then pick the amount of region you want out of them randomly. The second one is a binary space partitioning, where it tries to divide the whole map into, based on certain criteria, like here it says, any region should be less than 4 by 4 and shouldn't be bigger than 15 by 15. So it starts dividing over and over and over until it like this criteria is like fits, and after that it picks like the 3 region I specified in the number of regions. And the last one is the sampling, where instead of doing that, it just first it decides here is a region, and then if the region doesn't collide with anything else, it says this is one of the region. If it collides, it tries to move all the regions around it until the constraint is solved. So after we have the regions, we just have like these like meta stuff that says this is areas, different areas you can apply different algorithm on, but there is nothing. They still are parts, like everything inside it are unknown. And the explorers are the part where it tried to change like the map itself and get the generated map you wanted. So it's the core thing in our algorithm and in Marahel itself, and it uses an algorithm. So the explorer uses an algorithm to move over different tiles in a certain region or the whole map and try to modify them. That's why it consists of these 3 areas. The first one, which is the type of the explorer and the parameter. So the type is how it's gonna like visit the tiles in the map or in this region itself. And it could be random, like just visit random like tiles. It could be sequential, like each tile after the other, or it could be using kind of like an agent, that like random walking agent, where it walks in like north and then randomly change directions. The second part is the applied region. Should we apply it in the whole map, or should this stuff be applied on maybe a certain region or on all regions? So you need to define where the explorer will work on. And the last thing is the rules itself. And the rules are the things that modify like each cell on the map. So for example, here it says if you at any location, if you are solid, just change it to empty. And this is what caused the map down there. Like that was an agent and it's walking, and while it's walking, it makes everything like behind it empty. So like the rules itself, you can like put more than one rule, and the rules are consist of these 2 parts, which is conditions. And if the conditions happens, it will do something, like it will modify the map with a certain way. And as we see, the condition could be like a check your tile, check surrounding tiles, check distances to other tiles. They could also be the number of objects in the map, like different stuff. So this is another example where you have more than one rule to be applied. And right here it says like if you are solid and with probability 70%, just that's a mistake. It's supposed to be self-empty, so just put like the first one, 70% out of the time. If it's like a solid, just change yourself to empty, but there is 30% of the time, it will change it to like 3 by 3 empty. Like it's only not your location, but your location and all the surrounding location. And because of that, as you see, our like the previous one, digger, it changed it and it have a different like map generated. So this is how a complete script written in our implementation. Like every person can write his own implementation or his own interpretation for the language itself, but this is the way we did. And as you can see, like this script, it says it's going to generate a map between 30 and 50, and it's only have two entities, which is like the empty and solid, and it uses only one neighborhood, which is the old neighborhood, and it doesn't divide the map. And then after that, the first thing it goes sequential over the whole map and put for each tile, regardless what's its value, either a solid or an empty with equal probability. And the next one is kind of like a cellular automata, where it check each tile. If it's an empty and it's surrounded mostly with solid, it will turn it to a solid. But if it's a solid and surrounded with most empty, it will make it an empty. So we wanted to see what other script can we write besides this one script. So we wrote different scripts, and one just like use a binary space partitioning as the division at the beginning, and then just fill the whole map. Another one use an agent base which is just digging and making rooms in it, and this is what we got outside. And then this is the one I just showed before, which is a cellular automata. And then there is the last one, which is bind generator. And we just wanted to explore like just the layout of like maps for games that's like top down, like you can walk in all the direction, and it's supposed like you cannot dig through the walls, but we didn't add any constraint for that, and we wanted just to see if we didn't add for the cellular automata, will it be totally connected or not. So that's why the cellular automata is not connected. And we wanted to see are these like algorithms are very different from each other or not. So we decided to represent like a space for the generation for them, which we use two dimensions. The first one is the percentage of white space you have, like how big white space in the map, and the other one is the number of isolated objects. How, like for example, the binary space partitioning, it's like most likely it's very small amount of number isolated, because all the white tiles are connected and mostly all the black tiles are connected. So most likely most of the generated map will have a very few isolated object, but it has a very high percentage of white spaces. While when we look at the digger, it's different a little bit, because it has more like isolated stuff, because the digger can rotate around certain areas and make it like isolated, while cellular automata have the highest isolated areas, which like shows that cellular automata like have maybe object like parts of it that's not totally connected with the maps. And the last one, which I call it the mine one, which is like a mix between a binary space partitioning and cellular automata, and it could get like these small rooms that look like caves inside, and it's connected with corridors. So far, this is what we have done so far, and our next work is trying to integrate it with like Danish by Mike Cook, so we can analyze more about the generators that can be written in this language. Also, one of the things to integrate with the general video game AI framework, and with the tool called See-Through, where you can prototype different games. And the last thing is to build like a general video game level generator, because you're trying to generate a level generator for a certain game. So, and thank you. That was fast. I didn't expect it to be that fast.
I mean, that happens.
Yeah.
It seems to me that in this language, a very important concept is this concept of regions. So, do all games that you have considered, like Mario, have this concept of regions? Like, I don't see this region in a level like a platform or being as.
Yeah, like.
Would that be a limitation?
It's kind of a limitation for now, but we are trying to think like you can think like you don't need to divide as a region. You could say you don't have regions, and then you write your own generator down there using the explorers to do something constrained like Mario. Like you cannot have higher jumps and this like height, stuff like that. But so far, as you can say, it's a limitation. There is like other stuff like we have been working on to improve it. Like you can right now repeat certain explorers. Like you can write multiple different explorers after each other and say repeat all of them multiple times. So there is other stuff we are still thinking about. And if you have other suggestions to improve, just shoot me an email or tweet for me or anything.
Is there exactly one square, or do you stack things with layers?
I couldn't hear you.
In
Yes.
Would you mind repeating the questions just to make sure they get recorded on the live stream?
Okay, sorry.
No worries.
So he's asking if we can have more than one entity on each tile, or it's only one entity per tile. For now, it's only one entity per tile, but you can define an entity called enemy block, and this means this tile will have an enemy and block together, but it's just one entity in the end. Like we have a couple of previous versions we tried with where you can have like layers inside it in each tile, but it just went very complex, and so we decided to make it first a little bit simple, and then if you want to expand later, we can do that.
All right then.
Okay.
Let's have one more round of applause for our speaker. So now we have our next talk. Let me just find the dang. Yep. There it is. Cool. So take it away.
All right. Thank you. So my name is Santiago Antañón, and I'm going to present you some work that mainly done by my student, Sam Snodgrass at Drexel University. And I'm going to talk, same as the previous talk, about procedural content generation. And in particular, what we were trying to do in this work is, for the past few years, there's been a lot of work in machine learning-based procedural content generation systems that can learn, given a set of levels of a game, can learn a model of these levels and then use that model to generate new content for that game. But a lot of those approaches that use machine learning, basically what they learn is basically this very low level, what is the probability of a certain structure to be right next to another structure? These very low level tile correlation things. So we wanted to see if there was any way in which these approaches can learn higher level concepts in the game, such as how does placing a pipe in the case of Mario right next to a platform affect the gameplay in that particular game, right? And generate levels that take that into account. All right. So I don't think I need to go through these slides, but anyway. So procedural content generation is a field of study that studies the algorithmic creation of content. And there's been, of course, a lot of work in this area over the past, 20, 30 years, going back to like very, very early games, like in the early 80s, that were using PCG not for the sake of generating, but just because they didn't have enough memory to store the maps in the consoles or computers, so they had to actually generate them. But anyway, there's been work in generating things from stories or quests, like game objects and levels and maps. And in particular, in this talk, we're going to focus on generating levels for games. So there's been a lot of approaches that people have explored, things like evolutionary algorithms, like grammar-based approaches, fractals, all these kind of things. And as I was saying before, over the past, I want to say, maybe 5-6 years, there's been a lot of new approaches that are based on machine learning algorithms. Things like Markov chains or deep learning methods and Bayesian networks, all of these approaches that can generate new content by being trained on seeing previous content generated for a particular kind of game. Right. So what they do is, given existing data, they create a model, and then you can sample from that model to generate new levels. So the problem is that what we're trying to solve, as I was saying, is that these machine learning-based approaches focus on learning. I'm going to use syntactic and semantic, and probably they are awful terms to use in this case, but I'm going to go with those terms because they are in the slides. They basically focus on learning this kind of tiles. A certain tile tends to appear always after a certain other tile, or all of these low level, what things appear close to each other things in the levels we've seen, and then try to generate levels that follow the same distributions, right? And that is what I'm calling here syntactic, probably is a very bad term for that. So what we want to do is add, and again, maybe semantic is again the wrong word, but we want to add, I guess, gameplay information about it. Like, for example, in this particular screenshot, here is a screenshot of a game called Load Runner. Here you see ladders and there's platforms and ropes, and there's those white things are supposed to be gold pieces, even if they're white. So we can see, for example, a machine learning system would learn that those gold pieces always appear on top of a platform, right? Or that there is a piece of ladder always appears on top of another piece of ladder or on top of a platform. But it would not learn the fact that to actually complete this level, there needs to be a path that connects all the pieces of gold, otherwise the level is not completable, right? All of these gameplay information of the game is not captured directly by some of these approaches, like Markov chains or yes.
Does this extend past tile-based maps?
So far, everything we've done is in tile-based maps. When you say these, you mean this problem?
Your methods that you will...
Oh, so everything we have done so far is in tile-based maps. I think it can be generalized to other types of maps, but I don't know if it would be able to generate any kind of thing. Like, for example, we were looking at these Doom maps, which are like these vector representations, and that would be kind of tricky to represent in this framework. Maybe there's a way, but off the top of my head, I wouldn't know how to directly map it. So anyway, so this is what we want to do. We want to see if we can provide information to these machine learning systems so that they can learn this gameplay information, and then sample levels that take that into account. And I guess I already explained what this means, but what I mean by this semantic or gameplay information is that even if these machine learning models can learn that there's ladders tend to appear on top of platforms, they don't know what that actually means for gameplay, right? So can we actually tell the systems what does that mean for gameplay purposes? And what we're going to do is we're going to use this multi-layer representation. So let me just move one slide forward. So whenever you use one of these machine learning methods to generate for procedural content generation, you usually just give them this kind of a representation. Just this is how the level looks like, learn a model on this level, and then generate new levels. So what we want to do is add additional set of layers that capture different things. For example, that in this level here, that might be how the levels are, like the tiles are distributed in the level, but this is the path that the player needs to take to beat this particular level. And we want to add these kind of layers that capture additional pieces of information that might not be explicit in the low-level tile representation, right? So our hypothesis is that this multi-layer representation can lead to models that capture information that is beyond this syntactic what structures appear next to each other. And the question is whether using these multi-layer representations can actually help us generate levels for more complex games for which we cannot generate levels before. For example, in our previous work using Markov chains, we saw that it was kind of easy to generate levels for platform games like Mario, for example, but whenever you go to games that there's concepts like path that are very important, like for example in Load Runner, that paths are very important, then about 99% of the levels we generate are non-playable because there is no path, right? And the machine learning method has not actually learned these concepts. So let me just tell you very quick, in the experiments we did in this paper, which is the machine learning algorithm we used for learning these models. So we represent levels as basically matrices or arrays of tiles. So this would be the level, one particular level in Load Runner. So it is represented like that, where we have a matrix of tiles, and in every position in the map there is one particular tile, like block or empty or ladder or a piece of gold or an enemy, right? So this is the basic representation. And then what the system does, what this Markov chain approach does, is it trains the probability distribution of observing a certain tile type right next to other certain tile types, right? So we have I'm scared of moving away. I don't know if the camera would capture it. So we have, depending on the type of model we want to learn, we can learn different types of models. For example, if we learn this model, what we're learning is the probability that, let's say in one particular cell, there is a ladder, given that in the left of it there is empty, and below it there is a platform, right? Or we could learn the probability of certain tiles given only the one to the left, or the one to the left, the one diagonally down left, or the one below, right? And this is what the model basically learns, right? Given a level, it just learns these probability distributions, either that, this, or this. Or we could even have more complex models. The more relations you capture, of course, the more of the gameplay structure, the more of the game structure it can learn, but it has to learn many more parameters, so you need more training data, right? So there's a balance between the complexity of the model and the amount of training data you have. So once you've learned this distributions, then generating a new level is as simple as you start with an empty map, and then you start tile by tile from, let's say, from the bottom left, and you choose from the probability distribution that you learned one tile, you place it there, then in the next one, what is the probability of being here, a ladder or something based on the one you placed before, and you just keep placing tile by tile until you generate the whole level. So in particular for this work, we use a little variation of this algorithm that is what we call the VLR algorithm, which it generates a level section by section, and by sections, I mean you just divide the whole level you wanna generate in little portions. It can be arbitrary size. The size doesn't matter. You generate section by section, and after you've generated the whole level, you can provide some constraint that you want your level to satisfy. Like for example, I want this level to contain at most 10 enemies, and if any of the sections you've sampled violate some of your constraints, then you can remove it and ask the algorithm to just regenerate that section until the constraints that you provide are satisfied. Right? So this is the algorithm that we use. This is the baseline algorithm we use to compare our new approach. So what we did is, instead of just giving the algorithm this base representation, what we did is we generated these additional layers. In particular, in this paper, we considered 2 additional layers. So that is the structural layer, which is the basic one that the previous approach considers. We added a layer that contains the path that you need to follow to complete a level, including some of the actions you need to do. In this game, Load Runner, you can dig holes in the floor, so we mark the places where the player had to actually dig a hole. And we have an additional layer that just divides the map into regions, because sometimes in some games the probability of certain tiles changes depending on where around the map you are. So the model can actually have an intuition of where in the space of the map it is generating tiles for. And then to modify the Markov chain approach to take these multi-layers into account, the only thing we do is here in the bottom in the blue box, we just have the basic structure that we had before, the probability of a tile given the one to the left, the one below, and the one below to the left. So we add 2 more relationships, which is taking into account what do you have in each one of the other layers in that particular place, right? So it is like if you had, instead of a 2-dimensional array, you have a 3-dimensional array, and you sample depending on the tile you have to the left, below left, and also the tile that you have in the other layers, in the other dimension, right? So that, and then training works exactly in the same way. You just provide all of the training data, it learns the probability distributions, and to generate a new level, it does it exactly in the same way. So in the experiments in this paper, we used the game Load Runner, and in particular we used levels from the ZX Spectrum version of the game. It had like about 100 levels, or 100 or something, I forget exactly the number of levels it had. We used 10 levels from this version of the game. As I was saying, we focused on Load Runner because Load Runner has this additional concept of paths that makes it a little bit harder for these approaches to generate levels that are playable. And in this VLR algorithm that we use to generate levels, we only use one constraint, which is what we call the playability constraint, which is we try to generate levels that ensure there is a path. So we give that constraint to the algorithm. It would only generate levels that satisfy this constraint. And I'm not going to go into details of how the constraint works, but basically what this constraint does is, given a level, it checks that there is actually a path between all of the gold pieces in the level, because in this game, to beat the game, you need to collect all the gold pieces, so there has to be a path between all the gold pieces for the level to be playable. We just check for that. If any part of the level violates this constraint, that is resampled. I'm not going to go into detail on that. So as I was saying before, we used 10 levels of Load Runner, and for each one of those 10 levels, we generated 10 paths, well, 1 path per level, so we had 10 levels with their paths that indicate both the path and the digging actions. And this is, for example, one of the paths that we had. So we trained models with all of those 10 levels, and then we generated 50 levels using the standard algorithm that only takes into account 1 layer. And then we generated 500 levels using our multi-layer approach, 50 giving 50 for each one of the 10 paths we had. So when you generate a new level with our multi-layer approach, all of the other layers you have to provide, so it doesn't generate them. So we say generate 50 levels with this particular path. Now 50 levels with these other paths. Since we had 10 paths, we generated 500 levels, 50 with each path. Right? And these are just two more examples of the two of the paths that we had. And to evaluate how well did it work, we measured 3 things. The first is the percentage of levels that were playable. The second one is how hard was it to generate a level, which we measured how many times does this VLR algorithm need to resample a section of the level. And the last is how many of the gold pieces are in the path that we actually provided as input, right? Which is basically how much did the algorithm actually follow this path for generating a level. And here's just a couple of screenshots of levels that were generated. This is with the basic approach. That's with the basic approach. This was the multi-layer approach. Just from visual inspection, doesn't seem to be much difference. They're just load runner levels. If you have played load runner, they look like typical load runner levels. A little bit of confusion in some parts, but load runner levels tend to have these kind of messy parts anyway. So they look like standard load runner levels. And the results, and I just want to say that the results are not good. So just before going into the results, so this is the percentage of playable levels we got. In the very bottom, we have the percentage of playable levels we got with the standard approach without using this multi-layer, and we got 32% of levels were playable. We didn't get 100% even if we imposed this constraint of playability, just because the constraint we implemented in a way that it's sometimes some levels that are not playable sometimes pass the constraint just because of the way we implement it. So sometimes it generates levels that are not playable. Without the constraint, it would generate like a 1% of playable levels, so it would be off. And then using our approach, only 13% of the levels are playable. So it seems like we go backwards. And what actually happens is that with the different paths that we provide, we get different percentage of playable levels. So there's some paths that are actually very complicated. So it's actually very hard to generate a level that satisfies that path. So our approach actually struggles in generating levels that follow some of those paths. Right? But in any case, so playability results are not great. The other thing is, how hard is it to generate a level? This is the number of times our algorithm had to resample a section of the level, and in this we see basically no difference. So, and in the last metric, whoops, is how many percentage of the gold pieces of these in the level were generated in the paths we provided. And here, of course, not surprisingly, our approach does better. So 97% or 91%, I think 91% of the gold pieces in the generated levels are in the provided path. If you, with the standard approach, only 38% of the gold pieces would be in one of the arbitrary paths that we generate. So of course, in that respect, we do good. So at least one thing we can say is that using this multi-layer approach, at least we can control the types of levels we generate. But the conclusions, I would say, is in general, we cannot say that thanks to this multi-layer approach, we can actually capture more information as we wanted to. So the goal was to see if we could capture more of this gameplay information. I don't see any evidence that we achieved that. So I cannot claim that this multi-layer approach actually helps us solving what we tried to do. But at least one thing we can do is we were able to sample levels that follow the desired path, and it did not make the process more complicated. So it samples levels exactly in the same amount of time as the previous approach. So we can control it without adding additional complexity. And on the negative side, less playable levels were sampled because you are adding more constraints. You are providing a path. So for the future work, we still don't give up in this multi-layer representation. So we would like to see if maybe the layers that we provided are not the right layers. We just provided a path. Maybe there's other types of layers that we should have provided. So we would like to provide layers like that capture the enemy behavior. For example, when you spawn an enemy in a particular position, we would have a layer that captures maybe the path of this enemy, right? What does it mean to place an enemy here? That you are maybe blocking a certain area. Layers that capture some of this information, maybe that would help. And another thing that we didn't do with this approach in this paper is directly generate these layers automatically. So these layers were generated by hand and were provided by hand to the generator. We would like to see if we can extract them automatically, and also when sampling a new level, whether these layers, instead of having to be provided, if the model can actually capture and generate those additional layers on its own to generate a new level. We haven't done any of that yet. And that's it. Thank you. Yep.
Can you go back to the slide where you had the 50 and 500?
Which one?
Keep going.
This one?
Yeah. Could you just explain? So I'm a little confused on that. So you did 50 with single, and then based on those you did the 500?
No. So we had with the standard approach that doesn't even care about paths, we generated 50 levels, and then we had 10 training levels, and each of them had one path that we generated for it. So we trained with all of it, and then we say, now generate 50 levels that try to adhere to this path. And we generate 50. Now generate 50 more that try to follow this other path. Since we had 10 paths and we generated 50 with each, that's the 500.
How do you think your results would be affected if 10 was 100?
If 10 was 100? So that's a good question. So my intuition is that I don't think there's going to be much of a difference, because the models that we are learning are fairly simple. Like we don't have a lot of parameters to train, and with 10 levels is enough training data as for learning those parameters fairly well. Like in the paper we'll be presenting in the main conference, we did an analysis of the amount of training data you need to train these models, and for this particular model that we trained here, and the experiment was in Mario, not in LoadRunner, but with about 2 or 3 maps as training data, you already max out in the quality of the levels that you generate. So you don't need a lot of data for these models. Beyond that, it just flattens.
So as for what layers you ought to take, it does seem like a feature extraction function. Are you interested in some of the feature extraction approaches that are used in computer vision, for example? Since like a lot of evaluation of these models is like running sort of like eyeballing them. So something like a distance transform or side distance fields, or maybe something like line or border detection or something.
Right.
Right. We'd like to look at examination structural data, but also different stories.
Definitely, I think that would be very interesting. And so, as I was saying, in the future work, we are interested in exploring different layers, and one of them is aesthetic information. And we just wrote this line here in the slide, but we have no idea how to do that. But what you just said maybe is actually one way to do that. Like if we have some of these feature extractor systems that can capture things like, I don't know, symmetry or corners, or I don't know exactly what to. Right. So if we could have layers that capture some of these features, then I think that would be good, because that would give us like a more higher level view. I'm just going to leave it there, because I don't know, I was going to improvise what I was going to say. But definitely, I think that should definitely help.
We wanted to ask, so some prior work, including I think from y'all, has looked at incorporating like layer path tiles within what's referred to here as the structural layer. So I wanted to ask, why do this sort of multi-layer thing instead of just incorporating a layer path tiles like its own tile?
Right. So that is a good question, and I think the answer is that in particular.
Can you repeat the question?
Oh yeah. So the question was that in some of our previous work, instead of having an additional layer with the path, we actually just annotated in the same layer as we had the structure of the tiles. We annotated the path. We had the path as an additional type of tile. So we just have that particular layer with this path overimposed, and we just train with that, right? And we tried that, and I think people from UCSC as well tried some of these approaches. And I think the answer is that in this particular paper we use paths, a layer that was a path, and if you are just going to use a layer that is a path, I think maybe there's no benefit of having it as a separate layer. The only benefit would be that you are not
overwriting some of the tiles, like maybe the path would overwrite an enemy, because in this representation you can only have one tile per position. But in general, when you have more than just path and the structural layer, then I think that's where the advantage should be apparent. Yep.
You reported playability percentages for these levels.
Yes.
It's like if something has like a 5% chance of being playable, well, you just take two examples, and
right.
if you say that your algorithm includes that one extra loop, you can get whatever percentage you want.
Right.
In that sense, these things are effectively 100 with the extra loop on the outside. Is that a appropriate understanding of this?
So I didn't get. Can you repeat the question? I didn't get.
Sorry. So can you go to one of the slides that
yeah.
has the fraction of generated levels that are played?
There you go.
For any of these things, even when it's 4%, I would think you just restart your algorithm 100 times and keep the first one that finishes, and then you can get that number up as close as you want to 100.
Right.
So how should we interpret these? I mean, this is sort of, I guess, a success rate. So
right.
Very time to get that up.
Right. So the question is that even if we get like a small percentage, let's say 4%, something we could do is just run the algorithm 100 times until we get the percentage of playable levels that we want. So the question is, how should we interpret these percentages of percent playable? And I guess let me think if I know how to answer this question. So this percentage, so for example, 4% playability, it just means that out of the 50 times that we try to generate a level with our algorithm, I guess 4 means that only 2 of them completed. So we provide a limit of the number of times we can resample. So there's a bunch of constants that we define. So within those time bounds, we could only generate 4% of playable levels. So we could restart, do it 100 times. I guess what these percentages mean is how long would it, I guess what they represent is how long would it take until you get a playable level. If you can get 30%, that means that very quickly you will get a playable level. If you get 4%, that means you would have to repeat it many times. So it will take longer to generate a playable level. I guess you could always arrive at a playable level, but it will take much longer to get to one.
Suggestion then is consider playability as like I think guarantees playability, but the time scales with it. Because like if we're just mentally converting these numbers like one over that number at a time. Say that always means playable levels. It's just that sometimes it's 100 times longer than others.
Right. Yeah, I guess you're right. We could turn it around and just report how long does it take to generate a playable level and plot it that way.
Then there's no question of like why would people use it if it's not playable. They're like, well, as long as the number is economically low.
And sampling times are actually very fast. So when we say repeat it 100 times, so sampling a level with these approaches takes like 1/10 of a second. So repeating it 10 times would just be like a second. So it is actually very, very fast. So that is feasible. Yeah.
So this may be less relevant because you said you don't need a lot of path data, but have you considered using an AI to generate the paths instead of human generated? And then you can sort of close the loop and just let it run sort of endlessly.
Right. So the question is, so in this work we use human-generated paths. The question is whether we can use use an artificial agent to generate these paths automatically, and then we could just have like infinite amount of training data, I guess, for this. So in another piece of work, we have explored doing that, like learning from the paths generated by an artificial agent, and this was in the case of Mario, and we use an A-star agent that Adam Somerville from UCSC created. And one of the things we saw is that those paths are very, very different from the paths that humans follow. So we were trying to use those to generate levels that resembled more human paths, and we're not getting very good results just because the paths are very, very different. So this, unless we have an agent that generates human-like paths, I guess, if you had one of those, maybe we could do that. Like at least this A-star agent generates very direct paths, never goes back, which is very, very different from what a human would do. So when we try to generate levels optimized for that, then the levels look very, very different than what we generated for a human path. But definitely, if we had a good agent, I guess that would be different. All right. Thanks.
All right, with that, our first paper session is completed. So,
So we
yeah.
it's going to take till 10:30, and again, we are ahead of schedule. So break was technically from 10:30 to 11. AIIDE should be providing us coffee at 10:30, so we're going to hold out until 10:30 and then resume at 11. So you have plenty of time to go, grab a pastry from the counter down the hallway if you haven't eaten breakfast yet, or wait for coffee to come by.
And what that means for you, our viewers at home, is that we are going to be cutting stream at this point, and we will bring it back up at 11 for Mike Cook's talk on a vision for automated game design. See y'all in a bit.
Yep.